Alright, so this is problem 7.18 out of Taylor's Mechanics. Before I work through this problem, if you wouldn't mind please liking the video and subscribing to the channel. I'm trying to grow it, so I really appreciate that. And 7.18 is pretty similar to a previous problem we did before. We have this mass, this block M, hanging from this kind of pulley system. We're letting that dashed line be where the potential energy is 0, and we're calling that down direction the positive x direction. So with that in mind, let's go ahead. We want to find ultimately the acceleration. And to do that, we need to find, number one, the kinetic energy. So the kinetic energy, there's 1/2 m x dot squared. That's just it moving translationally. And then we also have 1/2 I omega squared, which is the rotational kinetic energy of the pulley system, because the pulley is rotating in this case. And the trick to these, whenever you have moment of inertia problems, is to remember that omega is equal to x dot over r. Well, the reason why we're doing that is because our Lagrangian should be a function of our generalized coordinate system, in this case x, and our generalized velocity, so x dot. So we want everything in terms of x and x dot. So that's why we're doing that. So in that case, we can write our kinetic energy as 1/2 m x dot squared plus 1/2 I over r x dot squared, and the r is also squared. Okay? So that's our kinetic energy. Our potential energy will just be minus mgx, it's just the gravitational potential. And then our Lagrangian, which is just the kinetic energy minus the potential energy, is going to be 1/2. Let's see, we can factor out the 1/2 from this. We can also factor out an x dot squared. And we're left with m plus I over r squared. And then plus mgx when we add our potential energy term to that. Okay, so now we can do our Euler-Lagrange equations of motion, which is the partial derivative of our Lagrangian with respect to our coordinate x is equal to the time derivative of the partial derivative of our Lagrangian with respect to the generalized velocity x dot. So dl by dx is pretty easy. That's just going to be mg. And that's equal to the time derivative of dl by x dot will just be x dot m plus I over r squared, because we're only taking the derivative of x dot. So the 2 comes down, the 1/2 goes away. And then taking the time derivative of that, you get x double dot m plus I divided by r squared. And then from here, we can solve for x double dot. And we can see the acceleration, x double dot, is just mg divided by m plus I over r squared. Okay, so that's it. I don't remember what the moment of inertia for the pulley is, but you just plug that into there and simplify. So that's how you do that. Hopefully that makes sense. And if it did, please like and subscribe.